now. So we will move forward to Professor Mark van der Laan's talk, Challenges and Advances for Longitudinal TMLE. Mark, please take it away.
All right. Yeah, thank you. Yeah, another paper comes to mind is Mireille Schnitzer, which also did a longitudinal analysis where she had to work with the cluster structure. But anyway, we can put that up. Okay, yeah, so I will talk about some challenges that, I mean, careful thought is necessary and being warned what can go wrong, in particular in these kind of longitudinal TMLE, and I will talk about responses to that as well as advances. So here's a little overview. We'll talk about the danger of overfitting the initial estimators. We talk about how to build a powerful superlearner, how to deal with positivity, and then some problems with the current sequential regression TMLE and how we can come up with another type of longitudinal target maximum like the estimator, and that's also work in progress, and we'll talk about that. And then finally, I will talk about a topic I've worked on over the last half year, and we'll talk a little bit about that. Okay, so first thing to realize when you do TMLE, and that it's not just for longitudinalism in general, if your initial estimator, so like your outcome regression, is overfitted, so that means there's little signal left in the residuals. Yeah, the TMLE works with the residuals, right? It uses the initial estimator as offset and says, okay, let me now see, fit that clever covariate with the epsilon and to get my bias reduction. And that has to do with, and if then the initial estimate is an overfit, there's very little signal there. So you don't really get much of a change. And that's why we, at the time, we saw that, for example, when you use random forest as your initial regression. That's a machine learning package where you can see there nowadays, more careful implementations which are better tuned, but the typical standard one, you can check that if you look at the empirical R-square of the random forest or the cross-validated R-square, that they're very different. Right? You might see a cross-validated R-square of 0.25, even though the empirical R-square is 0.7. Meaning it's really just doing a lot of extra fitting without any gain in performance. And these are dangerous algorithms for the sake of TMLE. And that's why we, in most of our applications these days, but not in all software developments, but we are trying to get implemented the so-called cross-validated TMLE. For example, in the TMLE package for point treatment, that's implemented and more. Which is the idea is that you apply the initial estimator, like the outcome regression, on the training sample, like 9/10 of the data. And then you do the targeting on the validation sample. And then in that manner, when you do the little extra fitting of the targeting step, the epsilon in front of the clever covariate, that is then getting its full power, because it doesn't matter that the initial estimator is overfitted, because you have now separate data to really still get the full bias reduction. And then you can then do it in 10-fold. So you get 10 of such targeted estimators, and therefore really 10 TMLEs, and you take the average of that. And then you can even, instead of doing the targeting separate on just the validation sample, you can actually pool across the targeting in one step and do the targeting based on a total cross-validated log likelihood. Anyway, so that's something to be aware of. Sequential regression in this longitudinal target maximum likelihood story requires particular care, since in that case we start running this regression first of the final outcome given the past, and then the next given the past, and so on. And the ones you start out with are at the end. So these are only conditioning on the people who are still in your sample, so who haven't dropped out yet and actually have also followed the regimen. Which is of course a long regimen at that final time point. So that means there are many fewer people still following your regimen and haven't dropped out yet. So meaning that you are actually fitting that regression on a relatively small sample potentially, And so there, if you then still use the same, aggressive machine learning, or maybe you throw in a linear regression with many covariates, even though they might make sense for the earlier, the regressions at earlier time points, they are just overfits for the final time points. And so that's why, again, you have to be very adaptive how you choose your machine learning algorithm, even as you move across time, because they should be very much based on the sample size, the effective sample size you can work with. That's also a reason why many of the machine learning algorithms, at least we like to use, are also using screening, so that we don't necessarily give them 1,000 variables. We might do some kind of variable importance, like that could be based on things like univariate regression, but it could also be based on some kind of lasso, or even a random forest has a little variable importance measure. And then you can rank the variables in that manner, and then only choose the top k variables, and then you might have different algorithms like that in your superlearner, indexed by how many, what the top k variables, how many variables are you including before you run that machine learning algorithm. So that helps to make the algorithm less overfit and actually more effective. Okay, so this also gets into that part of TMLE is to use, typically we like to use superlearners, because then we don't have to bet on one algorithm. So we don't have to say you should not use parametric regression, or you should not use random forest, or you should not use this. We often don't know a priori what's the best algorithm for this particular application, and that's why we like superlearner, because then we can build a library of all these algorithms which we think might be reasonable, and then just have a competition, an honest competition, decide what should be used in your data set. And that's all through an a priori specified superlearner, which is defined in particular by the library of algorithms. And so, but how powerful your superlearner is depends on your library. And so it is important to put good algorithms in there, and sensible algorithms. Like Maya was talking about, cluster randomized trials with 32 communities. We actually did do a TMLE, what Maya was referring to Laura Baltzer's work, where we did do a TMLE with a superlearner, believe it or not, but it wasn't superlearner, with 15 algorithms, but all of them using only 1 or 2 variables. So at the end, all of these algorithms did make sense given the sample size, and that's how there was a substantial gain in efficiency doing this. And similar, when you have rare outcomes, you want to make sure that even when you have 5,000 observations, if the outcome is very rare, so that there are only 50 cases, then your effective sample size is more like 100 or 150. So you want to use care in how you choose your machine learning algorithms, so that they are not overly aggressive given what they can work with. Another important thing about this library is that it should contain a range of algorithms going from parametric to highly non-parametric, to the point that it's still reasonable. And so that at least the cross-validate has an opportunity to choose the right kind of level of data fitting for this initial estimator work. And we talk here about both outcome regression as well as treatment mechanisms, sensing mechanisms, and so on. Another class of algorithms we have developed over the last a few years ago, which is highly adaptive lasso. And that's a particularly appealing algorithm because of its theoretical properties, but also of its practical performance, and also because it is actually a very, it's kind of does minimal fitting for a given complexity. So it's very robust algorithm. We'll talk a little more about that. I personally like the discrete superlearner, where we just choose the best instead of the best weighted combination, but then include in your library. You can still include convex superlearners, or which look for best weighted combinations, and in fact, in more recent work, we are actually suggesting to use for the meta learning step something like highly adaptive lasso, which is a much more aggressive way of finding the best functional combination of all these candidate estimators in your library. But then it's indexed by the L1 norm of your lasso meta learning step, and so we will have a whole range of them and then the discrete superlearner will just choose the best one based on cross-validation. And in this way, we are guaranteed, because the discrete is extremely good selector, very robust, we are guaranteed to find the right level of how to do the meta-learning step, right? From very parametric towards highly flexible. The highly adaptive lasso is an algorithm which, it's really a non-parametric maximum likelihood estimator. So you're maximizing, or depending on your loss function, it can be, you can think of it as a non-parametric least squares estimator, or whatever you're trying to do. So the idea is that you are saying, okay, I have this criteria, I have to minimize over all these functions, right? Like outcome regressions, for example, that's a function of the treatment and the covariate. And you have, let's say, a log likelihood or a least squares. You say, I want to minimize the least squares or maximize the log likelihood over all these functions, but under a constraint that they have to be so-called Cadillac, which is right continuous left-hand limit, but moreover, that they have a certain complexity. And the complexity is defined by the variation norm of the function. And I won't get into detail what it exactly is, but in essence, it is what you kind of would think of if you just plot a function and you see how variable, how much it goes up and down, right? And you count that all up, that's kind of a variation norm. And you're saying, okay, for a given variation norm, complexity of a function, I want the best function, which gives the best fit. Now that is, and then we just choose that variation norm, that level, that bound, that complexity, we choose that with cross-validation. So it can still be at the end chosen as large as needed, making the right trade-off of bias and variance. Now this estimator is remarkable. For example, we have shown that it achieves a rate of convergence. That means as sample size grows, it approximates the true function at a rate n to the minus 1/3 up to log n factors. And note here, this is not even looking at the dimension. The only way the dimension of the data kicks in is through the log n factors. So in essence, you get the rate n to the minus 1/3 for every dimension. So if you have 10 cohorts or 20, you get that rate n to the minus 1/3, which is, that's, I mean, that has all kinds of implications. That means in particular, if you use this highly adaptive lasso either by itself or in the library of the superlearner, you are guaranteed theoretically that these estimators like TMLE are going to be asymptotically efficient. So they follow the theory, at least asymptotically. And then on top, these algorithms are actually also very good in finite samples. What also we have shown about this highly adaptive lasso, it's an MLE, it's a maximum likelihood estimator or minimum loss estimator. And in particular, because of that, it solves a lot of score equations, just like a maximum likelihood estimator. And solving score equations means it starts behaving like a normal distribution, right? That's how you analyze maximum likelihood estimators. So this estimator is actually having that property what we are used to for parametric models, that if you use highly adaptive lasso to learn, let's say, your outcome regression, and you then choose the L1 norm, which is the same as the variation norm, because it just uses a big linear combination of basis functions, which are splines. That's what it comes down to. And you choose this L1 norm, instead of doing it with cross-validation, you choose it larger than cross-validation suggests. So there's a little bit of undersmoothing going on. So you choose more basis functions than you would normally choose. Then it actually has the property that it becomes something which is efficient for any features you calculate from that function, like the outcome regression. And that's remarkable. That means we have now a machine learning algorithm which acts like a maximum likelihood estimator. It gives you normally distributed features of that function. So it's a remarkable, robust machine learning algorithm. So it's not only converging at a remarkable rate, it's also having a remarkable, robust performance in the sense that it gives these approximate normal sampling distributions. And another beautiful thing about this highly adaptive lasso is that you can actually bootstrap it. You can use the non-parametric bootstrap, and you can prove that its behavior under sampling from the empirical distribution is still similar to as if you were sampling from the true distribution. Now, for typical machine learning algorithms, that's not true. And so that's why typically we say don't do the bootstrap when you do machine learning, right? And that's why we do influence curve-based inference. But with highly adaptive lasso, if we do that as our initial estimate and do the TMLE, you can actually fully bootstrap this. And that's good news, because that means you can pick up second order terms for the inference and get more robust variance estimates. Let's see. How am I going to the next slide? Oh, here. Okay, so let's, regarding dealing with positivity. So like Maya pointed out, you might have a treatment regimen which has poor support. So that means when you do this inverse weighting in your targeting step, for example, involving inverse weighting by the treatment mechanism, you are inverse weighting by this product over time points of conditional probabilities of following the rule, given you have followed it so far. And that product, if for some of these time points that probability is small, yeah, then you're getting this product might get really small. And so you start inverse weighting by relatively large numbers, and that can have all kinds of problems, such as large variance in particular. And so these kind of practical positivity violations, they can result in bias of your estimators, but also can mean that your variance estimator is underestimating the variance. And so a typical sample variance of the influence curve, which is what we normally use, becomes actually a somewhat biased estimator in these situations. So to deal with positivity violations, which means you have kind of weak support for your target estimate, and therefore you're subject to potentially high variance, that makes the estimators having problems and makes it challenging. And so that was also the motivation of doing a substitution estimator. It was the motivation for TMLE at the time. You know, I had worked a lot with Jamie Robbins and others on estimating equation methodology. And that was one of the findings, is that it's just not robust. It's not a substitution estimate. It's just too erratic and beyond other problems. And when you are a plug-in estimator, at least you will always respect, for example, that you're estimating a probability. So you respect the constraints which are about your parameter and also about your data chain distribution. But having said that, you know, it's not like when you do TMLE that suddenly it's not affected by positivity anymore. You still have, it's just not as crazy that it starts giving negative probabilities, but it's still, you know, it's still, it's a problem. And so there are other things for that reason, we have worked on, which is called collaborative target maximum likelihood estimation, where you say, okay, really the problem occurs because we are fitting this treatment mechanism, you know, and in a way that we start including covariates which make these weights blow up. And some of that is, yeah, makes sense. You know, you're trying to adjust for that confounder, but that doesn't make sense from a finite sample perspective, right? If you try to adjust for a confounder and by doing that, you increase the variance dramatically and probably not even gain bias, then it was not a good move. And so we really need a criteria, which is not only saying you should look at the fit of the treatment mechanism, you should, but really in criteria how to fit the treatment mechanism in a way that gives us maximal bias reduction during the TMLE step. Now that's exactly what collaborative TMLE does. It evaluates, like adding a confounder to your treatment mechanism or different candidate estimates of your treatment mechanism. It evaluates the performance of it, of how well it works in the targeting step in reducing bias. And so there's a lot of work on this collaborative TMLE, and in particular in these kind of observational studies where things get very challenging and you have these ugly confounders like almost instruments, we see potentially dramatic gains by using CTMLE relative to a blind TMLE, which just said, okay, I'm going to use the best fit of the treatment mechanism, even though maybe I start selecting a covariate which is extremely predictive of the treatment, but really is not helping me at all for bias reduction. That has also resulted in things like outcome adaptive Hall TMLE, where we use first highly adaptive lasso to fit like the outcome regression. And then all the basis functions selected there, these are the ones we bring over to the treatment mechanism and fit so that we are only putting in things which are predictive of the outcome in our treatment mechanism. And in this way, we can still tune that, and that results in very robust TMLEs, which hardly suffer and are much more careful in their bias variance trade-off. And so these are really exciting advances. And then there's also truncation, right? You always want to truncate. You cannot just run a TMLE and say, I'm not going to truncate. Same with IPTW, because that means you allow that one subject contributes, as much as the whole sample combined, and that's just unacceptable. So you need to truncate, like maybe by 0.01 or 0.025, that kind of standard things. But there's also a way to do it adaptively, and we have in particular using again this collaborative TMLE criteria to do that in work with Cheng Yu and Josh Schwab. We worked on evaluating using collaborative TMLE to do the truncation, and again showing great gains relative to other approaches. So these are the methods, the variations of TMLE, or the advances within TMLE, which allow us to at least deal with this positivity violations in an effective, sensible way. But then, as we also said, there's also the issue of variance estimation. That positivity also affects how good the variance estimator is. And so number one, the empirical variance of the influence curve is what we normally use. That should be replaced by the cross-validated variance of the influence curve, meaning you run your nuisance parameter estimates, like the outcome regression, the treatment mechanism, on training samples of 9/10, and you do the sample variance over the 1/10, and then you do that average across 10 splits, and that gives then so that at least it's not we don't get a low variance, because influence curves are like residuals, right? So if you have an overfitted initial estimator, you will be underestimating the variance. It's just like an empirical R-square is not as good as a cross-validated R-square. So that's why we have to use cross-validated variance of the efficient influence curve as a much more robust variance estimator, which is not just going to be small because you overfitted your initial estimators. But then on top, that can still not be enough, because the variance is itself a parameter of interest. And in essence, I'm saying we should be using TMLE when we estimate the variance of our estimator. And in others, we should be using a plug-in estimator, a substitution estimator. And again, that appears to be a very important thing to do, which really, for example, what Maya was talking about, that certain rare things like that, let's say the probability of receiving a treatment for a very healthy person is extremely small, and therefore it doesn't even happen in the sample. That would then cause that there are no large weights. But in reality, if you would have an infinite sample, these things would have happened, and you would have had these huge weights, and they would have contributed to the variance. And a plug-in estimator will pick that up, because it will integrate over all combinations of histories and not just the ones in the sample. And so that's where, again, and that's also implemented in the LTMLE package, and that's a variance estimator which will get large if there is real positivity issues. Another thing we have done, as I said, you can, when you do highly adaptive lasso as your initial estimates, you can actually do the non-parametric bootstrap. And so that allows us to also get wider confidence interval when that makes sense, and also picking up second order remainders. Okay, how am I doing on time? Let's see. Okay, so then there is something to discuss here about this. The TMLE Maya talked about was the sequential, is what we have been using a lot, and many people, is sequential regression. But there are some disadvantages of sequential regression, even though it's very convenient. The first thing is that you start with this first regression of the final outcome given the most recent past, which actually uses the least data. And that regression is going to be the outcome for the next regression. So that means the regression, which is actually the hardest, and therefore also the most biased and uses least sample size, is actually determining how good the next regressions can be. Because if this one is not good, that carries over to the others. So in essence, it corresponds with estimation of a likelihood factor at each time separately. So that's another issue. It relies on a discrete time formulation. because yeah, if you have all these factors of the likelihood over time, and you are estimating them separately at every time point, yeah, that means you need to have some events. Like, think about it, you're estimating some kind of conditional probability of what happens at that time point given the past. And that what happens is like an indicator of some type of event, yeah, then you're really estimating that without pooling over time. And so if you have very few events that are happening at that particular time point, because maybe it's a very fine time scale, it starts having problems. And so you really do rely on a finite number of time points so that there's enough happening between these time points. So that's another issue. The other thing with sequential regression is it really is made for mean outcomes, counterfactual means, and you can do it for the outcome at a particular time point, but you cannot target, for example, a treatment-specific multinomial distribution of an outcome at a time point. For example, maybe you have an outcome which has 3 possible categories, like you have in competing risks. Like you have an outcome of type 1 happening, or outcome of type 2 happening, or neither are happening. So these are 3 events. So you really want to estimate the probability on these 3 events under a treatment regimen and under a control regimen, and look at the difference to understand really what the treatment does to this important outcome process. Now, these are examples where you can still use the sequential regression by just targeting one probability at a time, but that means you get a non-compatible estimator. And so that is, has some disadvantages and some finite sample issues. And similarly, you cannot, you also have to separately target if you want to get the whole survival curve, the whole treatment-specific survival curve. Now, these are things which wouldn't be the case if we use actually what we really call targeted maximum likelihood, where you say, I'm just going to write down the likelihood as this product of conditional probability of what happens at the next time point given the past, and I am just going to estimate them. And so and then you have, for every factor is its own factor, you can estimate them separately. It's not like what happens to the loss factor, if that's less precise, that affects the earlier factors of the likelihood. That's not the case anymore, so that's good. They're all variation independent. They can all be fitted with their best possible superlearners. And also you can pool. You can pool across time now. And that means you can actually handle continuous time. So things where maybe people are monitored at times which really are, on a daily time scale. And maybe on one particular day, there are very few people who got monitored, but that's still okay, because we can pool across time and still do machine learning in that manner. And so this is work Helene Reitgard and Thomas and myself have been working on building such an TMLE. We had done that in 2010 with Ori Stittelman in discrete time, kind of type TMLE. That one was also a closed form. But anyway, now we have been extended it with Helene and are working on it as well, and also bringing in the highly adaptive lasso to get these longitudinal target maximum likelihood estimators in continuous time. There are also various challenges for scalable implementation. So that's something we also have been thinking about, in particular with Sei Wang and Lars, my son, and others, on really building the tools that we can start handling and make it, and that has big implications for all kinds of problems we are interested in, such as networks and time series, where we have to deal with this fact that these efficient illness curves are not easy, and they can make it very non-scalable to implement these estimators. But there is, again, highly adaptive lasso comes to the rescue. At least that's the approach we are following as a way to actually learn the efficient illness curve with machine learning, in this case with highly adaptive lasso, so that we get a real object, and that gives enormous benefits. Okay, so then there's this interesting thing that when you do target maximum likelihood estimation, the theory of it still relies on a second order remainder to be small enough, right? And that means some kind of product of like the propensity score estimator minus truth times the outcome regression estimator minus truth. So that's a square difference or product of differences. so we call it second order, has then to be smaller than n to the minus half. In other words, it has to be small relative to, like the standard error of your estimator. And of course, as the dimension grows of your covariance, that's even though asymptotically that's true if you use highly adaptive lasso in finite samples, this term might start dominating. And so the question is there a way to create a TMLE where that second order remainder is replaced by a third order remainder or a fourth order remainder? Now, this has been something people have been thinking about, like there's a lot of work by Van der Vaart and Robbins and so on. And we have done some work earlier on this idea of higher order pairwise differentiability and so on. But none of these methods could do it. But anyway, I think we now figured out how to do it. But it's, again, 100% relying on TMLE. It's not possible outside the TMLE framework. But again, TMLE has this unique thing that you can just start adding extra targeting steps and thereby create bias reductions. And if you do it in a very clever way, then it allows us to create subtleties, what we think now of as a higher order TMLE, which now only relies on like a third order or fourth order remainder to be small enough. So this is very interesting, exciting work in the making. And I really think this is going to give us an opportunity for, again, improved finite sample estimation and inference. And to just give you a glimpse of this, my last slide, some simulations Lars has been doing where you see, if you, for example, we make the first order TMLE is this one, and the second order TMLE is that one. And we did a simulation where the first order TMLE uses initial estimators which don't really get the right rate yet, like they have n to the quarter instead of smaller. So you see the bias is not disappearing at a root nth rate, but then if you do the second order TMLE, the bias is just negligible completely and it knocks it out. And suddenly you have then actually a situation where the first order TMLE is not able to get inference because it's not close enough yet, but the second order still is, because that relies on this third order remainder. So these are very promising results. Okay, anyway, I'll leave it at that.
Thank you, Mark. We are almost at the top of the hour, but I will open up for a quick question if something is there. I have one sort of little bit of, I don't call it concern, or maybe it is a concern, that when you show all these amazing possibilities, is it also somehow creating a new forest? That how is some of the beauty of it being relatively straightforward then disappearing in how do you choose between all these different ways of attacking?
Yeah, I mean, so this is of course always the tension between advancing the research, which is a continuous thing, which is always focusing on making it better and better and better, by trying to understand the weak spots, then starting to think about it. Why is this happening? Is it possible to do better? And that's why we came up with things like cross-validated TMLE, collaborative TMLE, and now this higher order TMLE. They're always inspired by saying, can we still do better? Right? Is there a way to do that? And then the beauty is that the TMLE framework has this flexibility. It's not just one method. The TMLE framework is a template. It's a template for constructing of efficient substitution estimates, which can have all kinds of additional properties by doing additional targeting. So it has immense flexibility. Now that immense flexibility is, from my perspective, a very good thing, because it allows us to deal with every challenge we kind of encounter. Having said that, there's also the practitioners, and the practitioners want to just get, kind of a story like, oh, hey, in this type of setting, I should be doing this. Now, I mean, and also our software is sometimes behind, right? We cannot some of these advances are implemented for some, but not for others. And so, so there will always be this little lack, but at the end of the day, also the software, and certainly when companies will get involved, right, who will start really working on writing these professional programs of software development, and the environment, it's not just the companies, also actually the whole, you know, there's so many now good R programmers, and they start getting involved. So it's not just us anymore, right? All kinds of people starting to contribute to this environment, adding these advances. So things will get better and better and better, also for the practitioners. But I do understand. I mean, we're talking, if you truly want to understand all this, that could be very confusing. But I think at the end of the day, it's good. Because we are making things better. And at the end, provide software which is more robust, more reliable for the people who really have to do this in their work.
I couldn't agree more. It was a little bit of a devil's advocate. But of course, we just have to not forget the point about at some point iterating it into the software. That was actually the best possible way of phrasing it. The thing that actually gets implemented in user-friendly, fully documented software. Now we are at the top of the hour, and I at least have learned very, very much and been very, very inspired from this, not just this day, but all 3 days, and all the speakers. I'm also just delighted to be part of this initiative. So I would actually like to close it now. Thank Mark, Maya, Lucas, Andrew, all the speakers. So yes, thank you very much. And for the people on this side of the Atlantic, have a wonderful weekend.
Thanks so much.
Thank you all for joining us.
Yeah, thank you.